So lesson 31-3 is going to talk about area and perimeter of regular polygons. So we're going to develop a formula and then use it to solve some problems today. So make sure you have your Springboard book. We're starting on page 457. So we're going to start off with a new vocabulary word, and that is an apothem. So an apothem of a regular polygon is a perpendicular segment from a midpoint of a side of a regular polygon to the center of the circle circumscribed about the polygon. Now that's kind of a very wordy definition, so let me try to explain a little bit what that is saying here. So we have this regular polygon, meaning all sides are congruent. Our apothem is a perpendicular line. Okay, here's our apothem. That connects to the midpoint of the sides of a regular polygon. So that makes it kind of a perpendicular bisector. It cuts it into two. Now, what it's talking about with a circle is that if this is the center of my circle, circumscribed means that all the vertices would touch, okay, the outer point of a circle. So we have all these vertice points here. Here. Okay. So if we look at, we have all these different radii on this circle. So we know all radii are congruent. Okay. So we kind of have this picture here that I'm going to kind of make the same exact thing here, but it says, consider this template of a regular hexagon. It wants us to draw radii from the center, okay, of the circle to each vertex of the hexagon. So it's going to look something like this. Okay. Now, if we have to find, question B says, what is the measure of each central angle? Well, we can find the measure of each angle here, central angle meaning these angles. I'm going to try not to kind of draw over myself. Okay, but all of these angles in here. Well, we know this is a regular hexagon, so all of these arcs here that we have are going to be the same size. Okay, because if we circumscribe a regular hexagon in there, they're all the same. Well, since we know a whole circle is 360, we have 1, 2, 3, 4, 5, 6 arcs in our picture. That makes each central angle 60 degrees, because we know in a central angle, it's congruent to that arc that it opens onto, right? So we know that each of these is 60 degrees. Now, if we wanted to find the area of this hexagon, what we can do is find the area of each triangle, okay, and use that to find the area, because if we find the area of one triangle, we know the area of all 6 of them, and we can just add them all up. Well, let's talk about the apothem here. How does the apothem of a hexagon relate to the triangles that we formed? Well, remember, the apothem goes from the center and is a perpendicular line that heads to the midpoint. So if we're talking about our apothem here of our hexagon, that is also the height. Okay, it's the height of our triangle. Okay. So let's look at a picture here. So if we have these triangles, we have in our apothem, we can find our apothem by finding the height of our triangle. So it says in question E, find the area of a regular hexagon with a side length of 4. So I drew a regular hexagon here on the side. So if it's saying the side length is 4, remember regular hexagon means all the side lengths are the same size. So we can think about this as a hexagon that's inscribed in a circle with an apothem down the middle, cutting this into 2 congruent parts. So if those parts are congruent and the whole side length is 4, we know that each piece is 2. 2 and 2. Now we also found that our central angle, this angle here, was 60 degrees. Well, when we drop our apothem, that's going to make each of these little angles 30 and 30, right? So in order to figure out the height of our triangle, aka our apothem, okay, of our hexagon, well, we have a 30, 60, 90 triangle here. And we know in a 30, 60, 90 triangle, our short leg is x, our hypotenuse is 2x, and our long leg is x root 3. So since this short leg is 2, I know my height, which is aka my apothem, is 2 root 3. Okay. Well, if I find the area of this triangle, let's just do this. Okay, the area of our triangle, we would take 1/2. Our base, remember the whole base of this triangle was 4. So 1/2 of 4, okay, times 2√3. Let's do this in a calculator. So we have 1/2 times 2 times 2√3. Okay, we get about, let's say, 3.5. So the area of our triangle, we'll say, is 3.5 feet. Now, the question didn't ask us to find the area of a triangle. It asked us to find the area of a regular hexagon. But remember, in this regular hexagon, I can draw multiple triangles here. One, another one, another one. But with all the radii of that circumscribed circle. So if we count this, we have 1, 2, 3, 4, 5, 6 triangles. Well, if the area of one triangle is 3.5, that's the area of all the triangles because they're all the same length because it's a regular polygon. So the area of our hexagon will just be the area of our triangle times 6 because we had 6 triangles. Let's just do this in our calculator. Times that by 6. We get about 20.8. 20.8 feet squared. Okay. So again, I found the height using this 30, 60, 90 triangle, this right triangle we get from dropping that perpendicular bisector. And then using the properties that we know about 30, 60, 90 to get the height. That gives me one triangle, but in a hexagon, we'll have 6 of those triangles. So I just timed my answer by 6. Okay. So we can kind of use this idea to find the area of any polygon. Okay, if we have a regular pentagon, we can look at this as having 1, 2, 3, 4, 5 triangles. Okay, or a regular octagon, if we draw all the radii coming from the center, we would have 8 triangles. So how many triangles are formed when we have an n-sided polygon? Well, we'd have n triangles. Okay. Now, what's the measure of each central angle? That's going to be important because when this angle here, all of our central angles will kind of help guide on how you can figure out the apothem in each regular polygon or the height of each triangle. Okay. So really what you just have to do is take 360 and divide it by how many sides you have. So in this regular pentagon, okay, for example, 360 divided by 5, each central angle is 72. In our octagon, 360 divided by 8 sides, each central angle would be 45. Okay. So there is an easier way to find the area of these regular polygons besides finding the area of all these triangles, and it's this formula here. Okay, so the area is equal to 1/2 A times big P. Now, A is standing for your apothem, so the height, okay, or that perpendicular line, where big P is talking about your perimeter of your polygon. So instead of finding the area of each little triangle, we can find the perimeter of our polygon, times it by the apothem, and then cut it in half. So let's actually look at a problem on the next page. So the hexagon problem we looked at used special right triangles because we had a 30, 60, 90 triangle. But in a problem like this, where your central angle was 45, if you cut that in half, you're going to get that this right triangle has a measure of 22.5 degrees. Now that's not a special right triangle. So the only way to figure out what the height is then to get that A value is to use trig. So sometimes we can use special right triangles. Sometimes we can use trig to find that A value, that apothem. Okay, but let's practice a couple problems here together. So on the try these A and B, I'm going to actually do those on the next slide because we're going to need a lot more room for this. But it says to calculate the area of a regular pentagon with a side length of 12. Okay, so here's I just need a little bit more space. So I drew in a pentagon here. Pentagon is 5 sides. So to find the area of the regular pentagon, again, we can think of this as we'll have a central, okay, a central point. Our apothem we need for our formula is going to drop from that point and cut this into two congruent parts. That's perpendicular. Okay. So now it said it had a side length of 12. So that makes each of these pieces 6 and 6. So what's important to kind of do here is think of this as a right triangle. Okay, well, we'll have a big triangle and then we'll cut it into two right triangles. But in order to do any triangle operations here, we need the measure of this central angle. Remember, to find the central angle, you take 360 and divide it by how many sides you have. So that makes each central angle 72 degrees. So if we find the central angle, we cut that in half, and we can know that each little angle here then is 36. Remember, we have to find our apothem, our A here. So let's just look just at that right triangle. You know, we have a side length of 6 here, 36. We are trying to find our apothem, the A. Okay. Well, 36 is not one of our special right triangles. So the sides don't have any special properties together. So when that happens, we need to use trig to figure out the length of our missing side. So let's look at what we're given here. If we're using our angle 36, we know the opposite side and the adjacent side. Well, which trig function uses opposite and adjacent? It's tangent. It's our TOA. So our tangent of 36 is equal to our opposite side, 6, over our adjacent side, A. Now you can rearrange this formula to solve for A. Remember, you can kind of think of that as tangent over 1. But A should be equal to 6 divided by the tangent of 36. Okay, so we're going to need our calculator for the rest of this. Make sure if you click mode, make sure you're in degree mode before you do any trig functions. But we have to just do 6 divided by the tangent of 36. We get about 8.3. So that means our apothem, our A, is approximately 8.3. So I need this for my formula. The other thing I need to find in the formula is our perimeter. So let's do that next, our perimeter. Now, perimeter means you add all sides. Well, remember, this is a regular pentagon. So if one side is 12, that means all sides are 12. So we can just honestly just take 12, times it by 5, our 5 sides, and get our perimeter to be about 60. So now I know my apothem, I know my perimeter, I can find the area of this regular pentagon. So we would take 1/2 our apothem times our perimeter. Okay, so let's just put that in our calculator. Times our apothem, 8.3, times our perimeter. So we get about 249. And what did they say here? It's 12 meters, so meters squared. So it is a little bit more work to find that A value, that apothem, but again, just use properties of special right triangles when you can. Okay, so let's try another one. Find the area of a regular hexagon. Hexagon means it has 6 sides with 18 centimeter sides, so 18. I might actually make this bigger for us so I can draw on it. Okay, so again, we're going to use that idea of some triangles here. So we have our central point, and we're going to form a triangle like this. And we'll drop the apothem from that center point to the midpoint, making this 9 and 9. Okay. Now remember, we need that central angle here. So the central angle is 360 divided by how many sides you have. In a hexagon, we have 6 sides. So that means we have a 60-degree angle here, making each little right triangle a 30-degree angle. Okay, so let's see, our right triangle now. We know our apothem is our height here. We know this is 9. We know this is 30. So we can either use trig again if you want, or because this is a 30, 60, 90 triangle, we can use the relationships that we know about a 30, 60, 90. Remember, this is x, so this has to be x root 3. So our apothem here is 9 root 3. Okay. So the only other thing I need is my perimeter. So perimeter, if we know one side is 18, again, we know all sides are 18, so we could just do 18 times 6. What do we get? 108. So our area of our regular hexagon is 1/2 9 root 3 times 108. So let's just throw that all in our calculator, and we are done. 1/2 times 9 root 3 times 108. We got 841, let's say 841.8. And what's our measurement here? Centimeters. So centimeters squared. So sometimes it helps me when I have my picture of my figure to draw that little right triangle on the side, because then I can label it a little bit more clearly. Okay. So I'm actually going to have you guys try one of these on your own. So it's on the lesson practice number 7. So you have a pretty big, we have a dodecagon. Okay, so count how many sides you have. It's giving you one side length of 20. So what I would do is we have our central, okay, here, our little triangle. So figure out your central angle, so that way when you drop your apothem, you can cut it in half. And then use a little side right triangle to find your apothem. And this would be 10, right? To find your apothem, and then use the formula 1/2 your apothem times your perimeter. So go ahead and try 7 and see what you get. So first start by finding the perimeter, that might help, and then you can find the area. Okay, if you did everything right, you should have got that the perimeter was 240. Okay. So then you will get your apothem. So 1/2 your apothem times your perimeter. This is the answer I got. So as long as you have something close, you might be off by a little decimal. That's approximately what the answer is. So let me show you my work a little bit here. So I just redrew that triangle. So I got that the central angle was 30 degrees, making each little angle here 15. Now, since 15 is not a special triangle, you have to use trig. So I did the tangent of 15 is equal to 10 over A. So if I solve that for A, it should be 10 over tangent of 15. So I got my apothem to be approximately 37.3. So plugging everything into my formula then is how I got my answer. So we will practice this much more in class. The hard part of all these problems is figuring out that length of the apothem. But just remember, you're just using special right triangle properties. So either 30, 60, 90, 45, 45, 90 triangles, or trig.